All right, well, good morning. Thank you and welcome everyone to the State of Utah Energy Storage Summer Webinar Series, which is held Wednesdays between July 8th and August 12th, 2020. My name is Kevin Brooks. I'm the Energy Analytics Manager for the Governor's Office of Energy Development. This webinar today is being recorded and will be shared after the series concludes in August. Presentations from today will be shared at the end of the week with the attendee list. Presented by the Department of Energy Office of Electricity Energy Storage Program in collaboration with the Utah Governor's Office of Energy Development, Sandia National Laboratories, Pacific Northwest National Laboratory, Mustang Prairie Energy, Quanta Technology, and the University of Utah's Utah Energy Smart Lab. Energy storage is the key to unleashing the power of renewables and providing greater grid reliability and resilience. Join us in exploring the pathways for increasing energy storage in Utah. So today's webinar will cover energy storage economics. We will have a keynote introduction from Dr. Laura Nelson. We'll have a presentation on energy storage applications and value stacking from Ray Byrne. And then we'll have a presentation on using analytics to improve the value proposition for energy storage from Patrick Balducci. And we'll also have an introduction to the speakers from Dr. Zhuk, the Director of the Energy Storage Program for the Department of Energy Office of Electricity and the sponsor of today's series. So without further ado, actually one housekeeping note, we ask that you keep yourselves muted throughout the presentation and hold your questions until the question and answer discussion at the end of the webinar. With the exception of any questions that you have for Dr. Nelson, Dr. Nelson will be taking questions immediately after her presentation. So if you have questions, please save them for that time or message them to me, and I'm happy to ask them on your behalf through the chat function. So with that, I will turn things over to Dr. Laura Nelson.
Good morning, everyone. It's great to be here with all of you today. I see my presentation is up. It looks like it might be on my last slide rather than my first slide. So do I have control, Kevin? Can I fix that?
Yes, you do. I apologize. And while you're fixing that, let's just give a little background. Dr. Laura Nelson, an economist, has led a distinguished career in the energy industry and is a long-standing hydrogen champion. Under her leadership, Utah founded the first of its kind annual Utah Governor's Energy Office Hydrogen Symposium. Prior to joining the Green Hydrogen Coalition, Dr. Nelson served as the energy policy advisor to the Governor of Utah, Governor Gary Herbert, from 2014 to 2020, and was the executive director of the Utah Office of Energy Development. As a leader in the energy community, Dr. Nelson has extensive board and committee experience, including serving as the chair of the Utah Energy Infrastructure Board and chair to the Western Interstate Energy Board. Dr. Nelson holds a PhD in economics from the University of Utah. And so welcome, Dr. Laura Nelson.
Great. Thanks so much, Kevin. And again, it's just really wonderful to be here with all of you today. Very gracious introduction. And just appreciate the Office of Energy Development, DOE, the labs, and all of those who have brought forward this super timely and very, very important topic. So I'm going to go ahead and move on to my next slide, which is my intro. And I want to acknowledge that really I think we've had a unique opportunity here in Utah, and I was so pleased to be part of that and work with just great people at the Office of Energy Development to drive innovation in the energy space. And for those of you who don't know me, or maybe those of you who do, I am very passionate about energy, and in particularly, I'm very passionate about providing a clean energy future for everyone. And that means an energy future which is affordable, reliable, resilient, and provides a pathway for economic growth and, very importantly, jobs. And that's why I became very interested in the topic of hydrogen and green hydrogen. And again, just pleased to work with a great staff to deliver a robust conversation on hydrogen. So a little bit about the Green Hydrogen Coalition, where I currently serve as the executive director. Our mission is to facilitate policies and practices to advance the production and use, very important, of green hydrogen in all sectors where it will accelerate a carbon-free energy future. And our approach is really unique. What we do is we focus on project deployment at scale, and scaled production combined with offtake. And we do that because we believe that that will leverage multi-sector opportunities to simultaneously bring together the resources required to decarbonize our energy future and make sure that we have adequate production and demand in the space. So before I kind of go full steam ahead, so to speak, with why green hydrogen is so important, I want to just make sure that we're all on the same page with regard to what green hydrogen is. For the Green Hydrogen Coalition, we basically define green hydrogen as any hydrogen that is made from a renewable energy resource. So we really are all of the above on the applications and pathways for making green hydrogen, whether it's using renewable energy resources to power electrolyzers that split water into its chemical components of hydrogen and oxygen, or electrolytic hydrogen production. We also support biological production through reforming biogas and thermochemical applications as well. So essentially, any process that utilizes renewable energy to produce green hydrogen with no carbon emissions is what we consider to be a critical pathway to a decarbonized energy future for everyone. And in fact, we really think that green hydrogen is a super game changer. To just kind of put this in perspective, if you think about many of the things that we enjoy today, you know, our economy, our industry, our agricultural sector, our power sector, a lot of what we enjoy today has been fueled by low-cost fossil resources. And that is changing, and it's changing rapidly because there is demand today, and we'll talk a little bit about that, for a lower carbon energy future. And so that's why green hydrogen can be very, very important as we look at this low carbon energy and industry future. It is commercially viable. It can repurpose infrastructure and provide for jobs. Hydrogen is already traded today, so it can decarbonize a globally traded commodity. It's utilized in many, many sectors, so we can decarbonize many sectors. And specific to the power sector, as we see more renewable energy integrated into the system, green hydrogen can provide a solution to provide for that reliability and resilience in the power sector. So we really view green hydrogen as a super game changer because of its versatility and because it can be commercially developed and deployed across multiple applications: transport, power, industry, chemical, agriculture, and really I think we will find unlimited applications for green hydrogen going forward. So just to kind of further emphasize this point, hydrogen is used today. It's a 70 million metric ton, I believe is about the traded volumes today on an annual basis of hydrogen. And it's used, as I mentioned, in many, many sectors. The challenge is that 99% of the hydrogen that we use today is made from fossil fuels, either natural gas or coal. And a very, very small percentage of the hydrogen used then is made from renewable energy resources, or green hydrogen as we have defined it previously. So we think there are drivers for green hydrogen today. As we look at the transportation sector, I'm sure you've all heard about initiatives for electric vehicles or zero emission vehicles. And so definitely as we look at those transportation uses and providing for green solutions, decarbonized solutions in the transport sector, which actually can be a very, very difficult sector to decarbonize as you look particularly at maritime or trains or large fleets, very difficult to decarbonize, but green hydrogen can certainly be a resource across that sector. We talked just briefly, I mentioned the industrial sector and chemical applications. What we're seeing today really within those applications, and this is occurring globally, is that, there's a social license to operate, in fact, and I think that there are pressures to decarbonize across those sectors. And so they're looking at green hydrogen as a solution and providing for that clean energy and feedstock roadmap for the future. So, it's not to say that there aren't barriers. I think if you've heard about green hydrogen, you've probably heard some of the considerations around the barriers to accelerating green hydrogen production and use. But just take a look at what's happening across the globe today. Renewable resources, solar and wind, are becoming super cheap. And in fact, they are displacing other forms of power generation, in particular gas peakers or combined cycle gas turbines. And this trend is really considering as the cost of these renewable resources continues to decline, and I think even faster than people had expected them to decline. So you have probably heard that cost can be a barrier to deploying green hydrogen, but to the extent that these resources are used in the production of green hydrogen, the decrease in the cost of these inputs is going to be significant in reducing the cost of green hydrogen and make it a viable resource. In fact, most folks, most analytics are predicting that green hydrogen really is commercially viable, and it is on a trajectory to be the lowest cost. Today, I think probably a conservative estimate has been provided by IRENA. IRENA is an international renewable energy agency, and as a government agency, it does tend to be conservative, and it projects, in fact, that the cost of green hydrogen will be halved by 2050. We think that it can happen much faster than that, and in fact, there are other predictors out there that indicate that. And why is that the case? Well, because I think as we see these demand drivers, we see the cost of renewable energy coming down, and we begin to see the scale up and deployment of green hydrogen, that effectively we're going to see cost reductions. So let's just jump a little bit more into some of the demand drivers, and I think relevant to the conversation today. Renewable energy is an important part of a low carbon energy future. As I mentioned, our economy really has relied on fossil energy to provide this reliable baseload energy resource that's different from these renewable energies that we're seeing coming into the market today. I don't know if everyone on the phone is familiar with what's happening in California, but essentially at times of the day in California, there is so much renewable energy produced, predominantly from solar energy, solar resources, that they actually have to curtail those resources. Now, curtailing resources isn't necessarily a bad thing, but it's really when you get these uneconomic curtailments and you have these very steep ramp rates. In other words, you've got to ramp the system up and down very, very quickly, and that becomes a pressure and a risk to the system. This graph has been affectionately referred to as the duck curve. I'm not from California, but in addition to agriculture, I've heard some Californians say that their other big export is, in fact, the duck curve. So the reason for that is a lot of this low-cost renewable energy does get used across the Western grid. So it can be an important resource, but we really have to address the significant ramp rate. And storage is a very, very important part of that. And it's not just short-term battery storage, it's going to be long-duration energy storage that's going to be required to provide for longer duration shifts and seasonal shifts on the grid. So I want to just highlight that to do this, to really look at long-duration energy storage and how we're going to push this into the system, and green hydrogen specifically, we really need leadership, and leadership is going to be fundamental to seeing this happen. a big place where that is going to occur is on the regulatory landscape, because storage and green hydrogen provide just a suite of values, and that value proposition is significant. So if we can bring down the cost of green hydrogen, extend the utilization of green hydrogen for storage, and account for all of these additional benefits, I think that's going to address some of the hurdles in seeing broader deployment. So with that, I want to turn to what's happening today, because this isn't something that I think is just creative ideation. This is happening in the real world today. Across the globe, we're seeing ports in Belgium that are looking to utilize green hydrogen by 2025. We're seeing production in Canada that's going to be coming online in the next couple of years to inject green hydrogen into a gas pipeline. So we're seeing this move to utilize existing infrastructure, repurpose it to provide for a low carbon energy future. And that's happening right here in the West, in Utah specifically, with the reimagining of the Intermountain Power Plant and repurposing that existing infrastructure to support the demand for energy and power in California. So through leadership, as I mentioned, which is really critical, I think, to driving this future, we have through IPA and LADWP the emergence of a very significant and important project. And in fact, the Green Hydrogen Coalition is very focused on this project and breaking down policy and regulatory barriers to assure that this project is wildly successful, we'll say. So we're super grateful, of course, for all of the leadership to launch this project. The idea is today that this project will be online by 2025, and on day one, it will burn 30% green hydrogen, and so it will demonstrate large-scale thermal plant conversion to green hydrogen over time by 2045, 100% green hydrogen, and it will also demonstrate large-scale storage. So just kind of jumping into why that is the case, the IPP plant is sited here in Utah, and it is strategically located near some salt domes. These salt domes can be converted into caverns that can store hydrogen. And this storage capability is what really is a unique aspect and part of this whole equation, where you've got green hydrogen used in production, you've got it stored so it can be utilized when it's needed, providing for seasonal shifting as required, and you're providing this green hydrogen to California via transmission lines, so very utilizing existing transmission lines to move green hydrogen to load centers. So you've got it all. You've got the production, you've got the storage, and you've got the transport. And so it's a super important project to demonstrate green hydrogen and large-scale seasonal energy storage. In addition, we think that this can drive feedstock availability for many, many other sectors, including the transportation sector. So that's buses, it's cars, and other aspects of transportation, and really can be a game changer in realizing a decarbonized energy future for everyone. So today, green hydrogen is in fact the only commercially viable seasonal storage solution. We support all types of storage, and I personally think all types of storage are going to be needed. Estimates indicate that in the western United States, we're going to be capacity short in the very near future. Some predictions estimate as early as the next 5 years, we're going to be in a situation where we've really got to add a lot more storage to the system. But just generally speaking, by about 2032, we're going to need close to 50 gigawatts, of energy storage on the system, and a small portion of this will be needed from short duration energy storage like batteries, possibly compressed air energy storage, and also pumped hydro. But when we really look at the seasonal energy storage and shifts, we're going to need a significant amount of diversified large-scale energy storage. So we think that this is absolutely possible. And as you look at the levelized cost of hydrogen storage, that in fact, storage in salt caverns is going to be the lowest cost. But I do think it's important to note that hydrogen can be stored in other ways as well, in rock caverns, in ammonia through thermochemical processes, and also in depleted gas fields. So we're on the trajectory for this future. We're very excited about it. And green hydrogen is going to be critical to solving our grid challenges and meeting the energy storage requirements of the future. So that's it.
Well, thank you, Dr. Nelson. At this time, if anyone has any questions for Dr. Nelson, please either message me or unmute yourself and just ask them directly.
Yeah, I have a question. Hi, Laura. It's Steve Handy. How are you doing?
Hi, Representative Handy. Good to see you.
Yeah, good to hear from you. Glad to know what you're doing. That is very interesting. Would you repeat that again, that part about the 5-year? I was writing and missed that. You said in 5 years, in the next 5 years, we'll need a lot more storage. I mean, what's driving that additional need for that critical need for more storage?
That's a great question. Really, what is happening is the transition in the energy sector, and we could, I think, spend a whole day doing a deep dive into that. But the short answer, and I went over it very, very quickly, I think, is reflected in the California duck curve. You've got so much renewable energy penetration, solar and wind, at the same time that we're seeing decommissioning of fossil-based resources, predominantly coal, occurring across the West, but also combined cycle combustion turbines utilizing natural gas, as there are increased policies to move to 100% renewable energy or specific carbon targets across the West. So it's really because we're seeing this transition in the energy space, increasing penetration of renewable energy resources, and they can't get us all the way to that decarbonized future and still provide for, I think, cost efficiencies and reliability. And so storage really is the key to seeing that future.
That's terrific. I'll get to you offline a little bit too, but that's wonderful. Thank you. Thank you.
Yeah, Laura, can you hear me?
I can. Hi, Mike. How are you?
This is Mike Gravely from the Energy Commission in California. I'm curious. I know you know the efforts we have, but have you done any analysis? I saw your charts, and I would love to get a copy of your presentation. I think you know that we're doing quite a bit of research in hydrogen and where it fits for California's future. Have you done any analysis on the cost for seasonal storage? I mean, I'm hearing a lot on seasonal storage, and we are beginning to look at some of that analysis, but I'm struggling with the concept of storing energy in July and using it maybe once in December, 1 or 2 cycles in a 12-month period, where typically you have cycles per day or cycles per week. And so I'm just trying to see, it has to be some pretty inexpensive energy to be able to, sit there, not be used for 4 months and only used once or twice a year. So I didn't know if you guys had done any kind of seasonal economic analysis when it comes to these charts when you're talking about very large storage.
Also, that's a really, really great question, and another one we could really do a deep dive into. And I think that there are a couple of really short answers to that. I mean, there is always going to be this round-trip efficiency consideration, right? And so anytime you produce the energy, you store it, and then you release it again, there's round-trip efficiencies. I think that what we see, though, are two things. One is because these renewable resources, the inputs are becoming so inexpensive that round-trip efficiency challenge is not as significant as we might have considered it previously. Then secondly, we're really seeing the cost then of electrolytic production coming down And if we can be on parity with natural gas, which, I think we can reach in the next 15 years, that might be aggressive, but I think we can get there, that seasonal energy storage for green hydrogen is going to just make a lot of sense. So happy to maybe get together with you offline and go into some of the more economic aspects and analytics behind those assumptions.
Thank you very much. And just one comment for you. I think we've had this discussion in general. One of the areas I'm very interested in researching is that we are very actively looking offshore wind in California, and with the capacity factor of offshore wind is very, very high, and so there's a potential for quite a bit of energy available for hydrogen production. So I have a research team looking at it, but I'm very interested in and so is some of our commission within the concept of, if we were to set up, and we're potentially looking at something as much as 4 gigawatts on the West Coast, and we have a particular site that already has 4 gigawatts of transmission available, and putting a hydrogen generation capability right there. So I would like to, later offline talk with you, but I'm very interested in you talking with the people that we have doing the research at Navigant, to understand if we tried to do that and we're able to get that much offshore wind, how would hydrogen fit right there on the coast, and could we generate, hydrogen? And if we did, how would we transport it? But I think if the offshore wind happens, and there's a lot of effort to make that happen, it all of a sudden it generates this opportunity to have a huge amount of electricity there available, and generating hydrogen seems to be one of the top priorities that we might be able to do with that. So it does make your charts look realistic if you're able to generate a huge amount of hydrogen every day, and then use it for seasonal storage could become a factor, because now you're getting all this and you really don't want to pump it or ship it or drive it if you don't have to. But I'd be interested in a follow-up with you and just understanding your thoughts of what type of system could be set up on the coast, and should the hydrogen be done on the site or be done at the wind, at where the mills are, and those types of questions. We're just trying to figure out, if we had that configuration, how would hydrogen play for that particular scenario, given the fact that we're trying so hard to get that offshore wind approved and permitted.
Hey, I would love to visit with you about that. They're definitely doing this in Europe today because of the significant amount of offshore wind that's being developed there. So I think there are some, best practices, but also, every location is unique. So I would love to chat with you about that and how we create that modeling and evaluation to support green hydrogen production combined with offshore wind.
Okay, thank you.
Hey, Dr. Nelson, this is Patrick Balducci with Pacific Northwest National Laboratory. So I wanted to, can you hear me okay? Good. So I just wanted to, in response to the last gentleman's question and comment in this discussion, we recently completed a project for the Massachusetts Clean Energy Center, and we're developing it further for the Hydrogen and Fuel Cell Technology Office at DOE. And it's a tool that's now online, and it was a multi-sectoral, analytical tool. So effectively, we had multiple pathways for the hydrogen to go. We model electrolysis, and then that can be used for either transportation fuels or industrial gases, or injected into a natural gas grid. We allow the user to vary the admixture limits. We have a methanation and cavern storage capability and the ability to adjust the costs associated with each of those. We have emissions profiles built into the tool. We have a final report that we've recently issued on it, and the tool is available online. We build in, I think, 4 different price structures, either operating in a distribution system with energy provided by distribution utility or by municipal utility, or operating as a transmission connected asset in the wholesale energy market as a municipal utility. And we allow the user to evaluate different clean energy incentives, including carbon taxes, low carbon fuel standards, and grants and accelerated depreciation and other things. And it basically takes several minutes to run, and then gives you the present value costs and benefits of each scenario. In our report, we evaluate 82 scenarios. So you can vary the prices of the energy. You can vary the emissions profiles of the generators providing the energy. It provides a significant degree of flexibility. It doesn't include fuel cell technology because of the round trip efficiency losses. In any of the scenarios we evaluated, it wasn't nearly cost effective to provide the energy back to the grid, but we're building that in for the work that we're doing for DOE. So I just wanted to make everyone aware of this tool.
That's great, Patrick. I'd love to visit with you more about that too. And I mean, we definitely support that fuel cells are an important part of the overall solution. As you look at grid resiliency, specifically, I think with microgrid applications, and also I think as an opportunity for backup generation today. So I'd love to visit with you more about that as well.
Sure. I'm happy to help. And like I said, the tool's available online. It's really hot off the presses. We finished it just about 3 weeks ago. So it's a new tool.
So can maybe Kevin can make that link available to all of us.
Absolutely. Yes. Thank you, everyone, for your questions. And yes, the presentations and links like Patrick has mentioned here, I am happy to provide after the webinar wraps up today. So with that, we will be moving forward. Thank you again, Dr. Laura Nelson, for the presentation and the questions and discussion. And Dr. Imre Zsuk, Director of the Energy Storage Program in the Department of Energy's Office of Electricity and sponsor of the State of Utah Energy Storage Summer Webinar Series, will be providing a few remarks on the energy storage economic speakers coming up. Dr. Zsuk.
Okay.
Excellent.
Hello there. That was very pleasant. Thank you, Laura, for telling us about hydrogen. And it illustrates that it's going to take everything we can do in order to get to a decarbonized, renewable, sustainable future. It's not just batteries, it's a whole host of technologies. And they all will have their particular time scale and their particular role to play. Now, in the last of these webinars, last week, we had an introduction to energy storage and an introduction to the policy issues involved, because policy issues are essential. This time, we are going to dig more into the actual business cases. This is going to be much more detailed in many ways. We're going to have two speakers, both of whom were supported by the Office of Electricity, my program in energy storage. And they have somewhat different approaches, but they're all valuable analytic studies and tools that are being used to evaluate real projects. Both Ray Byrne and Patrick Balducci have tackled projects that we have undertaken and shown how you can derive value from these cases using stacked value streams. And without further ado, here are Ray and Patrick.
Well, thank you, Dr. Zsuk. And as you said, Dr. Raymond Byrne will be providing us with a presentation on the energy storage applications and value stacking. Ray is manager of the Electric Power Systems Research Department at Sandia National Laboratories, where he has been employed since 1989. He holds a Bachelor of Science in Electrical Engineering from the University of Virginia and a Master's in electrical engineering from the University of Colorado, and a PhD in electrical engineering from the University of New Mexico. He also completed a Master's of Science in Financial Mathematics, Financial Engineering at the University of Chicago. Previously, he was a distinguished member of the technical staff, which is limited to a maximum of 10% of the engineering staff at Sandia. Awards include 2001's Time Magazine Invention of the Year in Robotics, the Prize Paper Award at the 2016 IEEE Power and Energy Society General Meeting, and the IEEE Millennium Medal. Byrne was elevated to IEE Fellow in 2017 for contributions in miniature robotics and grid integration of energy storage. So without further ado, I will turn this over to Ray.
Thank you, Kevin. Can you hear me?
Yes, I can.
Okay, so my talk is on energy storage applications and value stacking. And as Dr. Zhuk mentioned, all this work was funded by the DOE Office of Electricity Energy Storage Program, and we greatly appreciate their continued support. So energy storage applications, there are many of them, and there are different ways to slice and dice or group these applications. One common way is to break them up into energy applications and power applications. Energy applications occur over slow time scales, maybe hours to days or even months, and involve large amounts of energy. Power applications are on a faster time scale and often focus around real-time control of the electric grid and can happen over the course of milliseconds to seconds to maybe minutes. So this table just lists some common applications that we're going to review in this presentation. Under energy, we have arbitrage, renewable energy time shift, demand charge reduction, time of use charge reduction, transmission and distribution upgrade deferral, and grid resiliency. And then under power applications, we have frequency regulation, voltage support, small signal stability, frequency droop, synthetic inertia, and renewable capacity firming. So energy arbitrage is probably the most common energy storage application. If you just ask a random person about what they think energy storage can do, oftentimes arbitrage is the first thing that comes to mind. It's really simple. It's just buy low, sell high. These two plots show typical market prices in United and New England, and you can see you have some daily variability. Oftentimes there's a peak in late afternoon when folks come home, turn on the lights, get home from work, cook dinner. Sometimes you also have a double peak where you have a peak in the morning, which is like the chart on the left. So with energy arbitrage, you're basically buying energy when the price is low and selling when the price is high. And as our previous speaker mentioned, Dr. Nelson, that you do have to take into account conversion losses. So you have to reach a certain price difference before you actually start to even break even. And that's one of the misconceptions is that, people forget about that. And then also, because energy storage arbitrage is only maybe done for a couple hours a day, let's say you're just taking advantage of one peak in the late afternoon. Typical system might charge for 5 hours and then discharge for 4 hours. You're really only using it about 9 hours a day. So the utilization isn't very high. So that helps explain why the revenue is often not very high. But as far as efficiency, if you have 85% round trip efficiency, you have to have about 118% price difference just to break even. If you have 65% round trip efficiency, you have to have 153% price difference just to break even. So once your efficiency starts getting lower, you really need big price changes in order to just break even, let alone make money. In market areas, it's pretty well defined. You have market prices. In vertically integrated utilities, you can still do arbitrage, but really what you're doing is you're lowering the overall operating cost of your whole system. So if you can better dispatch your traditional generation, you can have cost savings on fuel and other things. And so it's really a savings in a vertically integrated utility, whereas in a market area, you're buying and selling, trying to make a net profit. There are also different variants. You can charge with inexpensive renewable energy. You can also participate in maybe the day-ahead and real-time markets, or just participate in the day-ahead only market. So this slide just shows some sample results for California. Here we used our software tools to model a 1 megawatt 4-hour system with 80% round trip efficiency and looked at 3-year total revenue by LMP node using 2014, 2015, and 2016 data. We actually completed a similar study where we're going from 2014 to 2018 this year. But first thing you'll notice is the color of the dot is proportional to the amount of total revenue over that 3-year period. For this analysis, we assume perfect foresight, which means you know the future, and that's the best you can possibly do. Without perfect foresight, you might get somewhere between 80 to 90% of this revenue for the day-ahead market. And the plot on the left is day-ahead arbitrage, day-ahead market arbitrage. First thing you'll notice is the total best node is around $150,000 for the 3-year period. You know, a 1 megawatt system, like 4-hour system, might cost $2 million to $3 million. So you're really not going to come anywhere close to breaking even with $150K in total revenue. The plot on the right shows for day-ahead and real-time arbitrage. First thing you'll notice here is the potential revenue is significantly higher. That's because of the volatility in the real-time market. But to try to engage in this type of activity is really complicated just because you have to sometimes decide whether to buy or sell a day in advance and for the day-ahead market and then make a decision, and then you don't know what the price is going to be in the real-time market until it actually evolves. So you have to have pretty accurate forecasting. And then there's also, you know, cases where you're buying in the real time, selling in the day ahead, and vice versa, or just only participating in the real time market. So even though on paper this looks like it's significantly better, it's also significantly more complicated from an algorithmic or forecasting perspective. And even still, 500K over 3 years, that's only a small fraction of nodes where it makes sense. A lot of the other nodes are much lower revenue, and it might not make sense yet. Renewable energy time shift is another energy storage application. So Dr. Nelson had previously discussed the California duck curve. So this will be the second mention of the duck curve. We'll see if Patrick mentions it in his presentation. But the general idea here is that the deployment of large amounts of rooftop solar have really depressed demand in the middle of the day. And then in the afternoon, as the solar rolls off and load increases, you have this quick ramp of required net load that you have to meet with generation. And that does cause a reliability concern because in the electric power grid, your load always has to match generation to maintain grid frequency. And if the deviations become too great, that can cause frequency, under frequency or over frequency events, and that ultimately might lead to blackouts. In CalISO, they've implemented a ramping product. In other areas, arbitrage is your only option. But the idea here is if you could move the renewable energy from the peak part of the day when it's generated to the later in the afternoon, then you'll be able to basically flatten the demand curve and make the operation of the overall power system more efficient and safe. And then just this slide is added because there are a lot of misconceptions about the capabilities of different storage technologies for long-term storage. So as Dr. Nelson mentioned, to attain the goal of 100% renewable generation, we are going to need massive amounts of longer-term storage. And one thing people often don't realize is there are trade-offs between the amount of storage, additional transmission, which provides geographic diversity and reduces variability, and then renewable curtailment. So when you're looking at expanding a power system or modifying a power system to incorporate more renewable or carbon-free generation, you have these trade-offs. Energy storage can easily store energy when it's not needed and then use it later when it is needed, and also help with the variability of renewable generation. Additional transmission helps reduce that variability, so it reduces the amount of storage required. And then, as the previous speaker had also mentioned, you can curtail, which means basically you're not using the energy for anything. And although that sounds really bad, it's really an economic decision. You know, what mix of energy storage, additional transmission, and curtailment will give you the lowest cost power system that meets your reliability requirements? But as far as longer-term storage, there's a misconception that lithium-ion batteries can be used for long-term storage. And maybe hypothetically they can be, but if you look at the example on the bottom of the slide, the Raccoon Mountain Pumped Hydro Facility is in Tennessee. It's a 1.6 gigawatt system that can store for 22 hours. So it's a massive amount of energy. If you do the math and try to recreate that system with 18650 cells, which are actually the basis for many large energy storage plants, you need about 20 billion cells, which would be 3 times the distance to the moon. So at some point, we are going to need massive amounts of storage, and just using lithium-ion cells might not be the right approach or most economical approach. As far as potential long-term storage technologies, some mature ones are pumped hydro, compressed air energy storage, and then thermal storage. And then promising long-term technologies include flow batteries and hydrogen electrolysis, but much more research is needed. And as the grid evolves to include more variable generation, we are definitely going to need more long-term storage. So I echo Dr. Nelson's statement. Time of use charge reduction is a behind-the-meter application, and this is just really arbitrage based on the rate structure. So some utilities have rates for each time period, basically have real-time pricing. Then you can have on-peak, off-peak pricing. So the idea here is you just basically use more energy when prices are low, and then use less when prices are high. For the same reasons as for arbitrage, this is often not a significant benefit. Then there's demand charge reduction, and this is a behind-the-meter application as well. Typically, in this case, your utility bill is based on your maximum rate of consumption over the billing period. So whatever your peak demand is influences your electricity bill. So if you have a load with narrow spikes, that can greatly increase your cost for energy. Narrow spikes are often caused by things like loads like pumping water, any type of big motors that you just turn off periodically and turn on periodically. So often this applies to light industrial type applications, but it can also be beneficial for more residential type consumers as well. And this can be a really big potential benefit. So in California, a lot of other places where there are demand charges, there are people deploying relatively small energy storage systems that can have a really fast payoff. Transmission and distribution upgrade deferral is probably one of the largest potential benefits from energy storage. The scenario here is you have some projected load growth that will make you perform a transmission or distribution upgrade. And that can include, reconductoring a line or putting in a new transmission line, or maybe buying a new larger transformer. Both of these can be very expensive propositions. So for a scenario where you have really slow load growth, you can use a relatively small energy storage system to defer deploying that new technology for a long period of time. You can actually have a really big benefit. So the potential benefit is proportional to how large the size of the deferred investment is, and then also how long you defer the investment. One challenge here is it's very location specific. Storage has to be located in the exact location of the grid to mitigate this one problem. And then another challenge is when you do the analysis, you'll often find that you only utilize your storage system maybe for a couple peak hours during the year, and yet it has a significant savings. And then oftentimes people will go look and try and find other things for the storage asset to do during the rest of the year. Depending on the degradation model for the storage system, this might or might not be a good idea. You might end up, using up the useful life of the system, performing activities that aren't really of high value, and then not be able to perform this particular application when you're required to. So you really do have to look at the overall model of what the system's going to be used for, including degradation. Grid resiliency is a really popular application for energy storage. Events like Hurricane Sandy and then Hurricane Katrina have increased the interest in this. And then also Maria in Puerto Rico. People usually use value of lost load to estimate what the resilience value of energy storage is. And this comes from two different places, either market prices or surveys. Lawrence Berkeley National Laboratory does most of the analysis on value of lost load. One challenge with this is the way they look at this data is they tend to break it up for different categories. And we recently did a project with Sterling Municipal Light Department in Massachusetts, where they wanted to procure a system primarily to keep power on to their first responders, police and fire department. And they ended up purchasing the system, but the resilience benefit using this type of information really didn't capture the true cost or the true benefit, because the closest category was data for public administration, and that likely underestimated the value to Sterling because it didn't take into account providing power to first responders where you might save a life. And then related to grid resiliency are microgrids, and that's just a combination of renewable energy storage and alternate types of power combined together. Energy storage is a key component. And then the operation of a microgrid as well as the design of a microgrid are both optimization problems. You want to size your generation storage so they meet load and meet your requirements, but you don't want them to be oversized because that basically costs more and makes it less economical. One comment on microgrids is they can significantly improve your resilience, but they do come at a cost. There's a common misconception that microgrids are going to provide lower cost energy than getting power from the grid. And in maybe a few scenarios where you have extremely high energy costs, maybe in Alaska or other places, this might be the case. But in the majority of situations where you already have to pay for the grid to be there, adding a microgrid can significantly improve your resilience, but it does come at an added cost. Frequency regulation is the second-by-second adjustment in output power to maintain grid frequency. And in this case, you follow an automatic generation control signal generated by the balancing authority that commands you to modulate your output power to maintain grid frequency. The plot in the bottom here is a Reg D signal from PJM, and that's a representative regulation command signal. PJM is unique in that they have a fast and slow signal, and the fast signal is meant for fast resources like energy storage. And so you'll see that over the course of this 1 hour period, the signal has many zero crossings, and then also it's a bidirectional signal. In this case, it goes up and down. So it's referred to as regulation up and regulation down. So implementation varies by different independent system operators. There's a bidirectional signal in PJM. In other areas like CalISO and ERCOT, they break it up into regulation up and regulation down. So depending on the capabilities of your system, you can just participate in one direction. The figure on the right is a 20 megawatt, 5 megawatt hour Beacon flywheel plant that's located in Pennsylvania. Pay for performance is a recent change over the last 5 years, where now there's a performance score. How well did you track your command signal? That's been very beneficial for energy storage because energy storage is very fast and good at tracking the signal. There's also a mileage payment, which is a function of the distance traveled. So if energy storage can better follow a fast signal that moves around a lot, it has more mileage and results in a higher payment. And then also there's a capacity payment that's being provided just for signing up to provide the service. These are some results from a study we did a couple of years back looking at PJM. And so we modeled the Beacon flywheel power plant, which is a 200 megawatt, 15-minute system. It's made up of 200 flywheels. And we looked at 1 year of market data and calculated the potential revenue from participating in frequency regulation and arbitrage. And the optimal policy was basically do frequency regulation all the time. So 98, 99, 97% was the time you're doing frequency regulation. The other small portion of the time, you're participating in arbitrage just to balance your state of charge. But if you look at this 1 year period, the total revenue was about $6 million. It cost about $20 million to build one of these flywheel plants. And this particular one went through a reorganization, so it was actually purchased for pennies on the dollar. So the new owners of the plant have probably done okay. One challenge here, though, is PJM's frequency regulation market. Because it has been profitable for energy storage, there have been a lot of new entrants. So if you look at the year-over-year potential revenue, it's been declining significantly over the last 5 years. And that's a challenge. The frequency regulation market is relatively small. It's only maybe 1 to 3% of the total size of an energy market. So, if it starts out to be really good for energy storage, eventually there's a potential to have additional market entrants, and then the revenue won't be as good for everyone going forward. Then there's voltage support. So typically you inject real or reactive power to control voltage. One thing that's beneficial for energy storage is that you can support reactive power over a wide state of charge range. It's really limited by the inverter rating, so it doesn't take much energy to do this. And then as far as compensation, some ISOs compensate for reactive power at the transmission level. It's mostly based on the opportunity cost of not providing real power, just because depending on your system, if you provide reactive power, it limits the amount of real power you can provide. One challenge here for energy storage is that there's a lot of competition. Pretty much any inverter-based resource can provide reactive power for voltage support. So solar-based rooftop solar has inverters. Any other type of technology that uses inverters can do this. And then another challenge is right now voltage is controlled usually by adding capacitor banks, and they're relatively inexpensive. So the value of this is still probably relatively low. And then it's also location specific. Most of the voltage control problems are in the distribution network, and so right now there really is no compensation mechanism providing voltage support in distribution networks. Small signal stability. This is probably a further out benefit of the next 10 or 20 years, but all large power systems have low frequency electromechanical oscillations. Usually they're in the 0.2 to 1 hertz range. And this figure shows a north-south mode in the western U.S. That's at 0.37 hertz, where the Pacific Northwest oscillates against the southeastern part of the grid, and then also Alberta. These modes are pretty fixed in their structure and frequency, so much so that they actually have names for them. So this is north-south B mode. There's also a north-south A mode. And the reason people are interested in these is the 1996 West Coast blackout was partially attributed to undamped inter-area oscillations. And so you can inject real power at different points in the grid to provide damping for these oscillations. Sandia and Bonneville Power Administration had a demonstration project where we looked at modulating the Pacific DC intertie to mitigate these oscillations. It was very successful. Energy storage is unique in that because it'll be distributed probably throughout the grid, for this particular application, you need to be in the right place to provide the right benefit. So there's a location-specific aspect of this. It's also nice for energy storage because the control signal that you output is relatively short duration, and then it's also high power but low energy. So this is a potential future revenue stream, but it's probably a long ways out. Folks are just starting to consider this. Frequency droop is basically generator speed control, and for a traditional generator, there's a control loop that's proportional to the frequency error. And so this is important because when you have a system that loses large generator or a transmission line goes out, your system frequency drops, and the rate of change of frequency is proportional to the inertia of the system. And then the frequency nadir, which is the lowest frequency reached after this event, is proportional to the amount of frequency droop in the system. So if you don't have a lot of frequency droop, the nadir is lower, and that will cause a lot of under-frequency load shedding and potentially lead to worse things like a blackout. Energy storage can provide frequency droop easily just with a control law. One challenge is how do you measure local frequency? Local frequency is, you're looking at the 60 hertz waveform, which is normally pretty clean signal, but when you have a fault nearby, that signal can become distorted. And so one of the research areas we're looking at is how do you estimate grid frequency in the presence of faults and other disturbances. But U.S. generators are not required to provide a frequency responsive service, nor are they compensated for providing the service. The Eastern interconnection suffers from a lazy L behavior, where when the grid frequency starts dropping, you basically get to your nadir, and then you bounce around at the nadir and keep going. So it's an L-shaped response. That's why they call it a lazy L. FERC has been looking at this. In 2016, they started looking at it, and by 2018, they'd issued FERC Order 842 that requires that all new generation must be capable of providing primary frequency response as a condition of interconnection. So they basically modified the small and large generator interconnection agreements. It still remains to be seen, though, how you're compensated. This just says you have to be capable of providing it. So energy storage can definitely do this and provide value to the grid. But there's still some questions about how to be compensated. Related to this is the synthetic inertia. Right now, large rotating machines provide the inertia for the grid. Inertia is important because it governs the rate of change of frequency after a generator drop. So as you lose inertia, the system frequency will drop much faster, whereas if you have more inertia in the system, that rate of change is slower. So inertia is good. It slows things down, which tends to make your frequency nadir higher. And by slowing things down, it also gives time for the system to react. So a concern with respect to inertia is that as we start putting in more inverter-based generation onto the grid, like wind and solar, it starts to displace the inertia provided by conventional generation. So you're starting to see reductions in inertia in many large power systems. Energy storage can provide synthetic inertia via control law. It's relatively straightforward. You just take the derivative of the change in grid frequency. Right now, there are no mechanisms for compensating resources that provide inertia. And then similarly to frequency droop, if you're using a local frequency measurement, you have the challenge of how do you estimate grid frequency in the face of a disturbance where the grid waveform might not necessarily be sinusoidal. And so how do you even define or measure frequency? And then so along those lines, if you, instead of relying on local frequency, you look on some kind of average frequency, you can improve the performance of the overall system because you're not following inter-area oscillations. So this is just simulation result of the Western power system with a double Palo Verde drop. And you can see these are different generator speeds, which represent frequency at different points in the grid. And they tend to follow a general path, but they oscillate about that path. If you take the average of these, and then you're not responding to these oscillations that are basically the inter-area oscillations. So implementing synthetic inertia with some kind of average system frequency, there are advantages, but then there are also disadvantages. To do this, you require communications, which adds latency, and then also makes you prone to communication issues. Renewable capacity firming just refers to the mitigation of the fast variations in output power that can happen with some types of renewable generation. So this plot just shows the output of a solar plant on a cloudy day, and so the nominal output power is green, but the actual is blue. So as different clouds come over, you have these steep drop-offs in output. So some areas are placing ramp rate limitations on renewable generation, primarily Puerto Rico and Hawaii. So meeting these ramp rate limitations is going to result in penalty avoidance. So this is a cost savings measure in most places. And the idea behind the control law is you have your renewable generation plant that has some output that's variable. You run it through a filter that calculates some power reference signal that meets whatever the specifications are for the ramp rate limitations. And then you look at the difference between that and your current output, and that's the output that energy storage can provide. So it's relatively straightforward to implement, and it's being required as more locations are putting limitations on ramp rates of renewable generation. So we talked a lot about different types of revenue streams from energy storage. The next step is how do you maximize the revenue from all these potential revenue streams? So you can formulate this problem as a linear programming optimization. The first step that we usually do is we look at the best possible scenario, which is perfect foresight. And that gives you insight into the operation of the storage system, like when it would charge and discharge in the optimal scenario. And that gives you a starting point for developing an operating strategy that does not rely on perfect foresight. And then the benefit of this approach is that it also gives you the best possible scenario. If it doesn't make sense with the best possible scenario, it's not going to make sense with scenarios where you actually take into account lack of perfect foresight, and the potential revenue is going to be less. In most market areas, frequency regulation is the optimum application. A notable exception, ISO New England. They have a forward capacity market payment, which is based on your coincident peak load hour over the whole year. And then they have a regional network services payment, which pays for your pool transmission in and out of ISO New England. And that's based on a coincident peak load hour each month. And these are both basically demand charges. So you can use energy storage to significantly reduce your payments into both of these. Grid resilience is a common goal, but value of lost load from surveys often doesn't yield significant value, and it doesn't capture the value of first responders. Another key thing about resilience is your definition of resilience is important. For the Sterling example, they want to be resilient to winter storms and hurricanes in the Northeast. For both of those events, you have a couple days notice they're going to happen. That gives you time to prepare and charge up your system and be ready for it. If your definition of resilience is to be resilient to just a random event like an earthquake, then your operation of your system is different. You basically have to have the capacity required for your resilience benefit on hand at all times. And that changes the way you operate the system, and then also makes the economics more challenging because you're basically just reserving your capacity for whenever this unknown event is going to happen at an unknown time. So I'll talk a little bit more about the model that we use. We use a relatively simple energy flow model. The state of charge at the current time step is the state of charge of the previous time step times the storage efficiency. And the storage efficiency just covers either losses from things like friction for a flywheel, or parasitic losses associated with maybe cooling for a battery system. Oftentimes, the storage efficiency we assume is 100% for battery-based systems, and for flywheel systems is maybe 85%. Then you have a term as the quantity of energy that you're recharging times a conversion efficiency, and then you have another term you subtract off the quantity of energy that's discharged or sold. And then you have constraints on the maximum charge discharge quantity in each time period, and then you also have a constraint on the maximum and minimum capacity of the system. And then in addition to the storage model, we define an objective function. And this is an example for CalISO looking at the day-ahead and real-time market. And basically you have a term for each decision variable. For instance, the quantity that you purchase or sell into the day-ahead market times the price associated with that activity. And then we have some cost terms that you can employ as well. Oftentimes we ignore the cost terms. Degradation modeling is an active area of research. One way to look at a storage system is you have a total throughput over the life of the system, and then it's really easy to come up with a cost associated with charge and discharging. And so you can use that as the cost terms in this equation. One pitfall with that approach is that it's a little more, the real system is a little more complicated. Your charge discharge cost or your throughput of your system is going to vary depending on how you use it. If you use a large number of shallow depth of discharges, you might get significantly more throughput relative to another application where you have very deep depth of discharges and they wear out the system more quickly. So trying to properly model degradation is still an ongoing challenge in the area of research. So these are the results that we saw previously, and the reason we're going to look at them again is just to compare them to frequency regulation versus frequency regulation and arbitrage. So the one on the left, bottom left, we're looking at 3-year total return for day-ahead arbitrage, and then one on the bottom right, day-ahead and real-time arbitrage. So notice here that the maximum or best case scenario for a node is maybe 150K total for the day-ahead arbitrage, and maybe 500K for the total 3-year period for day-ahead and real-time arbitrage. If you throw frequency regulation into the mix, you'll notice a couple things. So first, the revenue is better than just the day-ahead arbitrage, almost by a factor of 2. The other thing you'll notice is that the locational variability is decreased significantly. And part of the reason for this is that energy storage, for this scenario, doing frequency regulation is the optimum revenue stream. And in CAL-ISO, frequency regulation is zonal. So all the particular nodes down here in the south have relatively high revenue and not a lot of variation between the nodes. And that's because the regulation prices are zonal, and then regulation is the optimal activity. So that's an advantage from an energy storage perspective, and there's less location-specific nature associated with the revenue. And then up in the north, you see a little more variability, but it's still much better than compared to the previous slide, where there's a lot of more variability from just location-specific nature of the value of the storage. So this slide talks a little bit more about the Sterling application. So Sterling is a small municipal light department in Massachusetts, and they were interested in providing power to the first responders, basically their police and fire departments. The load for the fire department was really low. It was maybe 10 kilowatts, so it wasn't a large load. We considered several different value streams: energy arbitrage, reduction in monthly network load, which is based on a monthly peak hour, reduction in capacity payments for the forward capacity market, that's based on annual peak hour, grid resilience, and frequency regulation. The chart shows the different revenue for a 1 megawatt 1 hour system using 2017-2018 data. And so you can see here the forward capacity market obligation is about 45% of the total revenue for that year, and it's only a 1 hour discharge. So if you miss that 1 hour, you would lose 45% of your potential revenue. So because of that, we had some discussions with Sterling and started looking at what times of day these peak hours typically occurred. And then we ended up recommending increasing the capacity of the system so they could discharge during 2 hours just to make sure that they hit this peak hour. Then the regional network service payment is about 38%. We didn't put frequency regulation in this chart because Sterling decided for their own reasons they didn't want to pursue frequency regulation, but frequency regulation was on the same order of magnitude, about $100,000 per year for a 1 megawatt system. If you'd like more information on this, we have a paper out that's available on the Sandia website, and the link is at the end of this presentation. But one comment here: resilience was the primary goal, and it turns out that other applications really help pay for the system, and that's fairly common across other types of demonstration projects that we've worked on. The goal might be resilience, but oftentimes there are other methods that actually pay for the system. So these are just results from an optimization showing the operation of the system, and we'll go to the next slide that zooms in on the day of interest. So for this particular case, frequency regulation was the optimal policy. So the state of charge, which is the bottom chart, it hangs out about 50% state of charge during frequency regulation, and Q-reg is the amount bid in the frequency regulation market. So you're doing that all the time. And then you have to basically charge up because in this particular month, the monthly peak for the regional network services is right next to the forward capacity market peak. So you have to discharge for these 2 peak hours to capture that benefit. and then you go back to 50% state of charge, doing basically frequency regulation all the time. So this highlights one of the challenges with energy storage and value stacking. You have to charge and discharge at the appropriate times to capture each of the different benefits. And if you charge and discharge at the wrong time, you'll basically either miss the benefit totally or even incur additional expenses, which make the numbers even worse. So a lot of it comes down to a forecasting problem. And as you try and stack more and more benefits, it becomes more complicated as well. So even though people think, value stacking is the key to making energy storage more cost effective, there are challenges associated with it. And if a lot of finance folks that we speak with, if you have a scenario where you're trying to stack more than 2 or 3 benefits, they get a little worried just because it's a little too complicated, and they worry about you being able to execute and actually achieve that potential revenue. So this slide talks about valuing storage in a vertically integrated utility. The key takeaway here is that it's fairly complicated. So production cost modeling is the gold standard for valuing storage and integrated resource planning process. So really what you're doing is you're coming up with a very accurate system model that includes your transmission system, load variability, renewable variability, generator models, and then looking at what the optimal dispatch of your system is to result in the lowest cost energy to the consumer. And so this helps you primarily address how you do arbitrage reserve products. If you're looking at other energy storage benefits that require more technical analysis, this can include like primary frequency response or looking at deficient inertia. You have to do dynamic simulations, which are a different software tool. If you're looking at voltage support, you do power flow simulations, which can be the same tool as for dynamic simulations. Usually PSLF, PSSE, Powerworld are common tools. And then solar hosting capacity analysis and distribution networks requires looking at the distribution networks, and usually those are different modeling tools like SIME or OpenDSS. You also need accurate solar models or irradiance model or irradiance data for your system. And then transmission and distribution deferral requires load modeling. So, this covers most of the applications we've discussed in this presentation, but one thing you'll note is that every single one of these requires a different tool and a skill set to analyze. So it is difficult and challenging for vertically integrated utilities to look at a wide range of energy storage scenarios just because it requires different skill sets, different sets of data, different modeling tools. So as far as stacking benefits, you can stack benefits to increase potential revenue, but at the expense of potentially accelerated degradation of the energy storage system, and then also potentially increased complexity of the forecasting control algorithms. Modeling degradation is still an active research area because the charge-discharge profile will impact the degradation of the system. And then in summary, energy storage is capable of providing a wide array of grid services. The regulatory structure is still evolving for many applications. Different technologies are available for energy versus power applications, and then valuation of storage is highly location specific. For further reading, I'd encourage you to go to the Sandia website, which hosts the DOE Energy Storage Program's information on energy storage. There's a wide array of resources from papers to previous peer review results and other information. So it's kind of a one-stop source for energy storage information. So with that, thank you, and I'll open it up to questions, or should we wait till the end for those?
Yes, thank you, Ray, for that excellent presentation. We're going to save questions for the end after Patrick's presentation. And we are running a little behind schedule right now. So I do ask those of you who are able to stay beyond 12 p.m., please do. The question and answer discussion might run a little later than usual, but than we had planned today. But Ray, thank you again for that presentation on energy storage applications and value stacking. So moving forward, I would like to introduce Patrick Balducci, Chief Economist for the Pacific Northwest National Laboratory. Patrick has 25 years of professional experience as an economist and project manager. He currently serves as a chief economist at the Pacific Northwest National Laboratory, where he has been employed since 2001. He is currently leading the industry acceptance area of the PNNL energy storage program and has extensive experience in modeling and the benefits of energy infrastructure and in leading research and development efforts supporting the U.S. Department of Energy and the electric power industry. Patrick serves on the board of directors of the Pacific Northwest Regional Economics Conference. He holds a bachelor's in science and economics from Lewis and Clark College, where he graduated with honors, and a master's in science and applied environmental economics from the University of London, Imperial College of London. So with that, I will turn it over to Patrick.
Great. Thank you so much, Kevin. It's nice to be speaking with all of you today. I'm Patrick Balducci, Chief Economist at Pacific Northwest National Laboratory. First of all, I want to make sure everyone can hear me. Can everyone hear me? Kevin,
yes,
can
Patrick.
you hear me?
Can hear you loud and clear.
Great. Yeah. So new headphones, so they seem to be working well. If I speak too loudly, I apologize. But yeah, I'm going to give you an overview of some of the research that we're conducting at Pacific Northwest National Laboratory. I lead the energy storage analytics team, and you can see some of the contributors to my presentation there. I lead a team of many different engineers, different areas of expertise in terms of engineering, physicists, and economists working on energy storage modeling, economics, distribution system integration, control development, and all of those different areas of research. Right now, we are evaluating the benefits of energy storage at 16 locations around the United States. You can see that the power and energy capacities of these demonstration projects are 1.6 gigawatts and 18.2 gigawatt hours, respectively. Now, similar to the global deployment of energy storage systems, the vast majority of the power and energy capacity is tied up with two large-scale pump storage hydro projects, one in Washington State, one in Wyoming. We're also evaluating many different battery technologies and multiple battery chemistries, including multiple chemistries of lithium-ion battery systems and also flow battery systems. We're evaluating power to gas in Massachusetts, demand response programs in Hawaii. We're evaluating small modular pump storage hydro at 5 locations across the United States, ranging from Hawaii to Puerto Rico. And so as we've been tackling this challenging questions around energy storage, it really has built a foundation from which we've been able to expand what we do. So beginning with battery storage in the Pacific Northwest, we've expanded into multiple energy storage types and demand response and microgrids and distributed energy resources of many different types. And so it's been a very worthwhile and I think valuable evolution of our program. So we began by developing a taxonomy of energy storage services. Now, Ray did an exceptional job of highlighting existing and also some speculative or futuristic energy storage values. So the ones we have in this taxonomy are only those that we can really monetize. So there are additional values that aren't included in this taxonomy. But for each of these different services, we have defined methods and models for evaluating in markets and outside of markets. If you're in a market, of course, there's market revenue for several of these services. If you're outside of a market, typically you're monetizing the value in terms of avoided costs. And so we have 5 different categories of benefits: bulk energy services, including capacity or resource adequacy and energy arbitrage, which of course is buying low and selling high in the energy markets. The ancillary services, including those that are traded in ISO and RTO markets across the United States. Transmission services, including transmission upgrade deferral and transmission congestion relief. Distribution services, including distribution upgrade deferral, volt VAR control and conservation voltage reduction. And then customer energy management services. So those services that generate value behind the meter for customers. So we performed a few years ago an extensive literature review and conducted a meta-analysis. And you can see on the y-axis there the service value for several of the monetized services in the literature base. And the common metric here is dollars per kilowatt per year. So if you had a 1 megawatt, 4 megawatt hour energy storage system and you were obtaining $100,000 in capacity revenue, that would show up on the graph as $100 per kilowatt per year. And you can see the box and whisker plots here with a 25th and a 75th percentile here in the lower and upper bound of the box. And so for capacity, you see in most of the cases, it's an $80 to $140 per kilowatt per year. And I'll tell you in a few moments why that's the case. Arbitrage, the most logical value stream for energy storage, is actually one of the lowest value use cases in the U.S. Regulation tends to be much higher and generates significant value for energy storage systems operating in markets. The rest of the ancillary services, for the most part, are much lower. Transmission congestion relief, transmission upgrade deferral, and distribution upgrade deferral. The note I would make there is that in the vast majority of cases, there is no value. If you place an energy storage system in a distribution network, there may be no value or next to no value in terms of conservation voltage reduction, which improves efficiencies, the provision of reactive power and real power to handle voltage down in the distribution system. Often generates very little value, but in a small number of locations, the value is quite enormous. And so that's why you can see this huge variability with respect to the outcome for the distribution and transmission level benefits. Okay, so I won't spend too much time on these various use cases because Ray already did a great job, but I will identify how we monetize them. So I mentioned $80 to $140 per kilowatt per year for capacity or resource adequacy in most locations. Well, first of all, capacity markets have been established in regions throughout the United States. And so it's highly variable from one location to the next if you're operating in these markets. Now, these are forward capacity markets, so they're often clearing 3 and 4 years in advance. And in a place like ISO New England, they were clearing at $11 per kilowatt per year just a few short years ago. So that's actually $11 per kilowatt per month, excuse me. So it's a very large value stream. But in the most recent forward capacity auction, it cleared at $2 per kilowatt per month. So you've eliminated more than 80% of the value. So if you make an investment based on a prediction of future prices and an assumption that it would continue to be high in the future, that will be problematic. And so there's a significant haircut that's taken in your inability to predict future market clearing prices. That's been evident in a number of markets across the country. I'll mention PJM for frequency regulation in just a moment, but effectively you're contributing to that for all of us who have taken introductory economic classes. If there are significant profits to be made, then there are more market entrants. Effectively, they shift the supply curve upward, and you reduce the marginal point of equilibrium in terms of where supply and demand equal each other, the market clearing price. So for regulated utilities, you begin with about $150 to $200 per kilowatt per year in terms of the cost of a new entrant or the next best alternative for providing capacity. But you back out the energy and flexibility benefits, and that gets you down into that $80 to $140 per kilowatt per year range. In terms of the ability of an energy storage system to provide the benefits, you have to perform a loss of load probability analysis to determine the incremental capacity equivalent of an energy storage system. So for a 2-hour energy storage system, for example, the ICE or incremental capacity equivalent may only be about half that of a generator. So it might be 0.6, for example, as it was when we evaluated energy storage for Puget Sound Energy. And so all of this has to be factored into the assessment. So you begin at $150 to $200 per kilowatt per year, but it can dive as low as $40 to $60 per kilowatt per year, as it did for Puget Sound Energy. So frequency regulation, I think this was covered well by Ray. Effectively, there's a capacity payment, so you bid into the market. Energy storage systems get a full range of benefits. So when we bid this electrolyzer into the ISO New England market in the hydrogen tool that I just mentioned, it could operate anywhere from 2 megawatts to 10 megawatts, which meant you had to pick a point, a base point of operation, which would be 6 megawatts. So you only have 4 megawatts up-down capacity that is actually bid into the market, whereas a 10 megawatt energy storage system could bid in all 10 megawatts because you have a full range of 10 megawatts up and 10 megawatts down. In addition to that, you receive a very high performance score, 95% or better, typically. And you can see in this graph here that each of those green bars, if you add those all together, that's the mileage payment. So there's a payment for the energy that flows into and out of the energy storage system. Once again, the performance of the battery systems really are so exceptional, and the market's so shallow that if enough battery storage systems enter the market, they can actually solve the frequency regulation issue quite cost effectively, thus undermining their profit potential. And that happened in the PJM market, where the market prices effectively crashed. And so once again, there's a fair degree of uncertainty about future prices. Outage mitigation, typically measured in terms of value of lost load, but it can also be measured from the perspective of the utility in terms of penalty payments, so reducing those penalties, also reducing the lost sales of the energy that's not supplied during an outage. But what we do is we collect multiple years of outage data, and we create a statistically average outage year. And then we build those outages randomly into our optimization tool. And so basically, whatever state of charge the energy storage system happens to be in at the time of the outage, it triggers a response. And then our tool, using the interruption cost studies from Lawrence Berkeley National Laboratory, measures the with and without storage case to determine the marginal value of having that storage system there and serving that load that would otherwise be lost. This can actually be a fairly significant value stream for an individual energy storage system, particularly if there are commercial and industrial customers on the feeder that can be islanded. Residential customers, as you can see, the costs are $2 to $12 for a typical outage, up to 12 hours. So it's very low value. But when you start evaluating small and particularly large commercial and industrial customers, these outages can get into the tens of thousands of dollars, even higher in some cases, and I'll touch on that a bit later. Transmission and distribution, a deferral, once again, it's a present value calculation for those who've taken the introductory economic courses. You can see the present value calculation there. So in the numerator, the cost of the system, if you push it out, say 10 years into the future, will go up because of general inflation, cost inflation of maybe 2 or 2.2%. But in the denominator, you're building in the discount rate, which will typically be the weighted cost of capital for that utility. So that could be 6 to 8%. And so that's driving down the present value cost. So that's a significant value. And you can see here, so we have an example here where by installing a 4 megawatt energy storage system, we could defer the investment in a substation upgrade of about $10 million for 6 years. And with the weighted cost of capital being about 8%. In present value terms, you're bringing down the cost of that asset from an accounting perspective by $2.5 million or 25%. And there's another case that we'll touch on shortly that's a much larger value. So you cannot evaluate each of these services individually and just add them together. You have to go through a co-optimization routine. And so you can see energy price in the first panel to the left, and you can see it growing throughout the day and peaking in the evening before falling again. Now, if we were only providing arbitrage, buying low and selling high in the energy market, you can see what the battery system would be doing in the second panel there. Every time it's negative, that means it's charging. And then when you have a hat there around lunchtime, noon, and then in the evening, the battery system would be discharging. Now, if you layer in frequency regulation, you then deviate from that schedule, and you can see that in that third panel. And as you layer in additional benefit streams, you deviate from it further. So proper co-optimization analysis is required to reasonably estimate the value of energy storage, and it has to build in all the technical limitations. You can see the state of charge range always being monitored throughout the day. The battery storage evaluation tool at Pacific Northwest National Laboratory has a 24 optimization window that's updated on an hourly basis for all 8760. So that at the end of the one-year simulation, it will tell you the number of hours you'd be optimally engaged in the provision of each service and the value of each of those services. You can see the tabulation of that value for the graph to the right. And so effectively what this model is doing is it's solving a multi-dimensional co-optimization process with the objective function of maximizing value or revenue. So to the extent that you're using the energy in the battery system in 1 hour, there's less of it available into the next, and that has to be accounted for. While at the same time, you cannot serve all services simultaneously, and so decisions have to be made. Optimization has to be performed to realistically estimate the value of energy storage. Now, throughout the remainder of this presentation, I will discuss several pitfalls and challenges in accurately estimating the value of energy storage. So the first case study is Portland General Electric Salem Smart Power Center. This was a system built several years ago using ARA money. So it was extraordinarily expensive at the time, and the costs have come down quite considerably. It was a tremendous R&D project, but from a profit perspective or from a value perspective, return on investment perspective, it was fairly poor, as I'll show you in just a moment. It was also built to be quite a shallow energy storage system. You can see it there to the lower left, 5 megawatt, 1.25 megawatt hours. So that's an energy to power ratio of only 0.25, which means if you provide full power, it'll be fully discharged in just 15 minutes. So you can see the stacked benefits to the lower left. And the point there is that's technically unachievable. You're not going to simultaneously provide all 9 services. And in fact, 9 services is quite ambitious anyway. It's probably going to be a much smaller number of services. And in fact, we found out there was just a few, 3 or 4 services that were of any real value anyway. So when you co-optimize, you can see that you're actually eliminating about 28% of the benefits. You can see in present value terms, the benefits fall from $7.5 million to $5.8 million. So if you're not properly co-optimizing, then you're vastly overstating the value. You can also see here the benefits for various energy to power ratios on the blue line, and then costs that were measured in the orange line. You can see beyond a certain point, really beyond an energy to power ratio of 2 on the margin, the benefits start to fall, right? They're increasing at a decreasing rate. And so the costs are actually greater than the benefits beyond an energy to power ratio of 2. So that green line shows you the return on investment ratio. So even at a much more reasonable and lower costs built to today's standards, at today's costs, the energy to power ratio for an optimal system, optimally designed system would be 2.0. And so it's important that you complete these studies before you actually deploy the systems. Beyond that energy to power ratio, you're actually undermining profit potential, and below it at 0.25, you're doing poorly. And in case you're wondering about the actual investment, the cost of the system was in excess of $20 million based on the prices that were evident about 10 years ago. And so the return on investment ratio for this specific investment was quite low. So the Nantucket Island Energy Storage System is an evaluation that we recently completed for National Grid in Massachusetts. On Nantucket Island, there's a small resident population of about 11,000. But during a couple summer months, it's a tourist destination. The population swells to over 50,000. And so there's a couple of months and really only 200 to 300 hours out of the year where there is a capacity problem on Nantucket Island. And so the question is, do they build a third cable? You can see the graph there to the lower right, that would have to wrap around the island and connect at the Bunker Road substation at a cost of $150 to $200 million, or do you build a combustion turbine generator and a 6 megawatt, 48 megawatt hour energy storage system to handle local reliability issues and to defer an investment in that transmission, that line connecting Nantucket Island, which is 30 miles off the mainland, to the mainland. And so the decision was made to invest with online generation and storage capacity at a much lower cost. The cost of the generator was about $33 million, the cost of the battery system about $31 million, and when the full rate impacts were built into the pro forma, including all returns to investors, insurance, borrowing, and the like, the costs are about $93 million. So they understood the cost of deferring the value of deferring the investment in the transmission line, but National Grid didn't understand the full value of the system, and so we were hired to help them with that process, estimating that value and defining the operations of the system to take advantage of the landscape of economic opportunities. So the benefits of local operation, there are actually about 700 outages experienced on Nantucket Island over an 11-year period, so significant reliability problems. We actually modeled the distribution grid there on Nantucket Island. We took their SIME data and worked with it in OpenDSS and GridLab-D, and so we could actually model all of those outages. Now, we started off with the 700, but of course we weren't going to mitigate all 700, and so we broke it down to just those that we thought were potentially unresolvable through the use of on-site generation and the battery storage system. And through that process, we were able to whittle it down to fewer than 100 outages. And for those outages, we were able to actually simulate the outage and the use of the energy storage system and the CTG for addressing those outages. And actually, if investments were made in reconductoring of 4 lines to enable the full export of the battery system, its power and the CTG simultaneously, and automated feeder switching was employed in 4 locations on the island, we estimated that 46% of the customer minutes of interruption could be avoided, because although it was less than 100, the on-site generation could actually mitigate some of the most significant outages that were experienced over that 11-year period. And then deferring the investment in the transmission line, we conducted an extensive load analysis and stressed out that load to have a 95% sort of extreme scenario. And then we forecast that load into the future and estimated the number of deferral years at 13. And so the value of deferring an investment in that $150 to $200 million asset was actually exceeded $100 million in present value terms. So just the benefits of local operations generate an return on investment ratio of about 1.3, so it's quite a significant value. But we also took advantage of a recent innovation in the ISO New England energy market by bidding in the energy storage system in hours where it was feasible to do so, and we developed procedures for doing that and ensured we were in compliance with all requirements of ISO New England. And there with the continuous storage facility, effectively it answers the question, is the energy storage system a generator, is it a demand-side resource, or is it a regulation resource? And the answer in ISO New England now is yes to all 3. And that's correct. In some regions throughout the United States, it's still challenging to take advantage of the full range of capabilities of energy storage systems, although that's being addressed through some recent FERC orders and the implementation of those orders. So you can see here in the upper right there that you could operate as a regulation signal, and you can follow a energy neutral regulation signal. You can serve as a generator and providing energy, as you can see there in that orange line, and then serve as a demand-side resource as well, offering a spinning reserve. And the combination of those 3 signals creates that quite unique signal to the lower right there, but effectively you're being paid for the provision of all 3 services simultaneously. Now, we didn't assume perfect foresight here. We assumed imperfect foresight. So we used a statistical technique called the gradient boosting machine method with an ARIMA-fed sort of underlaying component to it. So effectively, we were predicting prices based on historic trends and weather forecasts, but then we were clearing on actual historic prices. So that showed that depending on the statistical metric that you used, that actually there was quite a significant divergence between perfect foresight and something that would be much more realistic. We also used the day-ahead market prices as a predictor of real-time market prices for that next day as well. And there were interesting results. Even using a simple method such as that, you could do fairly well in terms of capturing most of the benefits. But still, you're probably going to capture probably 10 to 30% fewer benefits than the perfect foresight prediction method. So when you add in all of the benefits of market operations and local non-market operations, you can see a benefit cost ratio, return on investment ratio of about 1.55 with total stacked benefits of just a few benefit streams of about 145.9 million, exceeding the revenue requirements and energy costs of about 93.9 million. Now, some of you may very well be recognizing that typically FERC would not allow a rate-based asset to also bid into markets because that would be effectively double dipping. But there's a memo that was issued recently that would allow that revenue to be brought back and used for the purpose of effectively dampening future rate increases for their customers. So as long as the revenue is being brought back to the customer rates, to the customers to which the rates are applied, then that could potentially be allowed. And so National Grid is in the process of developing or plans to develop such a proposal. Also, we have built into our annual operating plan to keep up with National Grid and show how the values are actually achieved in real time in future years. So in addition to the actual design study that we have conducted and our estimates that we've prepared, we're going to actually monitor the performance to show how well they did over time. So here are results of several recent economic assessments performed at Pacific Northwest National Laboratory on projects that I led as the PI. And I'll just highlight how different the results are from one location to the next. So Salem Smart Power Center, most of the value was actually tied to primary frequency response. So it's such a shallow energy to power ratio at 0.25, you can set aside a reasonably small amount of energy and provide an enormous benefit there to Portland General Electric. But with that said, you can see the value at $5.8 million and costs exceeding $20 million, so a poor return on investment there. For Puget Sound Energy Glacier, the vast majority of the benefits are tied to islanding a remote community near the Canadian border that's experiencing significant reliability problems. Opalco Decatur Island, the major benefit was using the energy storage system to reduce voltage and stress on a submarine cable, and we prepared an electrothermal model to estimate the extension in the life of that cable system based on the use of the energy storage system to reduce the stress on that cable. Energy Northwest and Northampton Microgrid, those were bill reduction benefits associated with either demand charges or capacity and regional network service fees. And then Avista Turner, that was a unique system that was deployed in the parking lot of Schweitzer Engineering Laboratories, and it's really designed to address reliability problems there. There were voltage sags they were experiencing. If the voltage sags were a significant enough duration and magnitude, their machines would shut off for at least 3 hours at a cost of $150,000 per hour, and on average that occurred twice per year. Now I will add that system that was deployed there was a new technology. It was a vanadium flow technology developed in Washington State, and it did fail. So after 2 years, it was disassembled, and they're in the process of replacing it. And so that happens as well. Some of the newer nascent technologies experience technology challenges, particularly newer vendors. And so we've actually experienced that with a couple of our vendors. So the battery testing program at Pacific Northwest National Laboratory, we've modeled battery systems and their performance and woven it back into our economic tools and our economic algorithms. And the way we do it is we begin with using the DOE-OE test protocol, and we perform baseline testing. Then we go through use case-based testing. So we try to model, what would a battery system be doing if it was operating at this location for this utility, getting into this specific regional energy market. And so we develop these use case-based tests that we think are quite realistic because many of the typical testing protocols and duty cycles that are prepared are kind of more perfect in terms of trying to extract meaningful test results, and so they're designed to test the battery system as opposed to being designed to achieve economic performance. And so with a use case based duty cycle, sometimes there will be long lags between the charging and discharging where you'll experience parasitic losses due to the auxiliary systems that are in operation, or they're operating during times and when temperatures are dropping or are very high, and those can also have a very significant effect. So they're not in a laboratory; they're out in the field, and so that creates a degree of realism here. And so you can see battery round-trip efficiency for 4 of the systems that we tested as part of our Clean Energy Fund work. And you can see the round-trip efficiencies changing quite significantly between a low discharge rate, moderate, and a high rate, and then being quite variable between lithium-ion battery systems and flow battery systems. So you may hear that a lithium-ion system can achieve 90 to 92% round-trip efficiency. But when you place it out in the field, you add auxiliary losses, and then you add economic operation and temperature fluctuations, it can drop into the high 70s to low 80s. And then for the flow battery system that we are evaluating, it could dip into the 50s in terms of the round-trip efficiency. So it could be quite low. And so if you're assuming that you're obtaining a 90% round-trip efficiency and bidding it into a regional ancillary service market, but you're only achieving, say, 75% round-trip efficiency, you can actually be losing money in the process. And so advanced understanding of the battery's performance really does generate a great degree of value. And to the extent that you don't build that into your optimization and your estimation process, you may be overestimating your benefits fairly significantly. We see the adjusted round-trip efficiency just for a specific battery system here. This is the Puget Sound Energy Glacier lithium-ion battery system, which was the best performing battery system that we tested. Most of the use cases that we evaluated, each of those little boxes is a week of testing. And for most of them, they're between 80 and 90%. But some of them actually dove quite low, depending on how long the rest was, the temperatures, and you can see the temperatures on the x-axis there. So if we extended this into higher temperatures, this battery system was on the Canadian border, and so the temperatures never rose very high, and really never beyond 80 degrees Fahrenheit, as I recall. But if it did with a lithium-ion battery system, it would start to fall again. So this is sort of misleading, this graph. Beyond a certain temperature, if you start getting into the 90s and 100, it would actually start falling again. So what we learned is that, and it doesn't look like this is activated, but typically it would be. And what you see are these curves that are at first diverging from one another and then merging on top of each other. What we found is that our ability to predict the performance of the battery system early on in the testing process was quite poor. In fact, we would often violate state of charge limits after about a day and have to stop operation, recalibrate, and restart again. So we developed a model, and we found that there were 4 statistically significant variables: state of charge range within which you're operating, power output level, whether you're charging or discharging, and temperature. And if you could accurately model these parameters, you could correctly predict the performance of the battery system. And so we built this filter through which the data would pass. We had 80 to 120 data tags passing in as granular as a second-by-second basis. So we're constantly updating our predictive capabilities with this through this testing process, and found that within a few short weeks we could quite accurately predict the performance of the battery system as it's used for a broad range of different use cases and in different conditions. The 5th parameter of note is state of health, which is sort of modeled exogenously from this, because we have to measure it over a long period of time. And so we've developed this process of evaluating the cells in the lab, so taking this bottoms up and also a top-down approach. And so we've had to build that into our models as well because you cannot exceed certain cycling limitations, and you don't want to continue trading in the market if, in fact, you're generating a very small value but eliminating 3 or 4 years of much larger economic profits in the out years. And so you have to build in effectively a penalty into your calculation for degradation to capture the full cost of the system. So the last thing that I want to mention here is our optimization, performance, and evaluation tool. What we learned is that the control systems that were deployed in the Pacific Northwest had some shortcomings. And so this effectively allowed a utility to perform a Monday morning quarterback. So you operate the battery system for a month, and then we'll simulate its operation for a month, show you the value that you actually generated for that month and the value that could have been generated if you had solved for flaws in logic or improved your forecasts or built a more dynamic understanding of the battery system's capabilities into your modeling structure. EA stands for energy arbitrage, EI for energy imbalance. And so you can see the blue bar is what was generated from the control system, and then you can see with the orange bar and the gray bar the improvements with enhanced understanding of your battery's capabilities and with improved logic. So we could show something that was certainly potential improvements, something that they could build in immediately. Improving forecast error, of course, is quite tricky, but we found systems that were set to resolve imbalances to avoid 10% penalties where there was round-trip efficiency losses of 20 to 30%. So every time they were using the battery system to resolve that energy imbalance, they were actually losing money. And so understanding the economics of these various use cases and the capabilities of the battery system is key to capturing those values in real time. So what we've learned is that siting and sizing of the energy storage system is exceptionally important. The value will change from one location to the next and across various energy to power ratios and scales. It's important to complete these design studies before you actually purchase and deploy the system. It's important to measure a broad set of use cases, but typically it will boil down to, say, 3 to 5 use cases that you can actually capture at real time. With that noted, if you have an estimate that excludes distribution level or transmission level benefits, you may be avoiding or may be missing a very large benefit. And finally, from one region to the next, the benefits differ quite significantly. And then within the Pacific Northwest, particularly, but across the United States, the utility structure will dictate value. So for PUDs and co-ops in the Pacific Northwest, they're, for the most part, Bonneville Power Administration customers, and they face very different value propositions relative to, say, vertically integrated investor-owned utilities in the Pacific Northwest. And then finally, accurately characterizing performance and then weaving that back into the economic optimization is really key to successfully estimating these benefits in a realistic manner and then capturing those benefits in real time. Finally, I want to acknowledge the leadership and support provided by Dr. Emre Juk at DOE and Bob Kirchmeier at the Washington Department of Commerce. And then here's my contact information. Feel free to reach out to me. I mentioned the hydrogen tool that we recently developed. We have several other tools and studies that you might find useful as you start digging into the energy storage question a bit deeper. But with that said, I guess I'll turn it back to Kevin, and if there are any questions for Ray and for me, I'm ready and prepared to answer whatever you have to throw my way.
Well, thank you very much for that presentation, Patrick. Excellent information there, as well as with the other presentations. So with that, we will open up our question and answer and discussion section. So at this time, if you have a question for Ray or Patrick, please unmute yourself and ask it, or feel free to send me a message. I'm happy to ask it on your behalf. All right. Well, I have one that has come in just via the chat. So Ray or Patrick, are the lack of market policies the biggest limitations to economic deployment of distribution level energy storage?
So, Patrick, do you want to go first?
Yeah, I'd be happy. Yeah, so distribution level energy storage is really challenging, right? In terms of understanding the value streams, in terms of getting the data and the modeling of it, it's so dispersed, and so and the utilities tend to possess all that data. So unlike an established energy market where there are locational marginal prices, and you can actually dig into the value of these various services established by the market, it gets exceptionally challenging when you get down into the distribution grid. So there's really a lack of available data and tools, and it's just such a dispersed value. Capturing that and understanding it is very challenging, I think.
Yeah, and I'll add to that. There's some other technical factors too. One is utilities don't even have good models of their distribution network, so just starting from a modeling perspective, that's a challenge.
That's right.
Then there's also competition. Other inverter-based resources can provide similar types of services. If you curtail solar, or you can actually modulate reactive power or real power. So there's a lot of competition with other devices. There's also the ownership question because, if you have rooftop solar that's owned by an individual, you have energy storage that's owned by an individual, then you have the grid that is owned by the utility, and they might have a tap-changing transformer or other assets in that distribution network that they control. Ideally, all these devices might have to work together to provide the best benefit, but then you have different entities that have to try and talk to each other and agree upon price for different things. And so it's a combination of technical and ownership, and then also policy-related issues.
Yeah, and even in for, let's say, a vertically integrated utility that's preparing an integrated resource plan, they're developing distribution plans separate from their IRPs, and so properly modeling their network and understanding those value streams, and then bringing them back and even including them in an integrated resource planning environment is typically, obviously, not done and would be exceptionally challenging. And so I think it's incumbent upon the modeling teams across the country and for us at the national laboratories to try to improve that investment process. So how do you, because if you think about an energy storage system and you're comparing it to a generator, there's a whole host of values for an energy storage system that would be missed in an integrated resource planning process. And so there's sort of an unlevel analytical playing field, and capturing that and bringing it back into that investment process is exceptionally challenging. But I think it's something that ultimately will be necessary for improving the efficiency of the investments that are made.
Excellent. Well, Patrick and Ray, thank you for answering that question. I had another one that came in actually back after Dr. Nelson's presentation, and just let me bring that up here. So Dr. Nelson briefly touched upon the Intermountain Power Plant here in Utah and converting it and developing energy storage at that site. And so the question asks, in terms of converting existing infrastructure and power plants into energy storage facilities, can you speak to what level this will affect property tax revenue in counties where the plant is located?
I don't know. Something off the top of my head. I haven't worked on any projects or given any thought to how investment, and I realize property taxes are typically addressed through the process of a development of an energy storage system and the building into the rate case. I presume to the extent that you're enhancing the value of the system or continuing to have value that in something that's already been otherwise amortized, the value might be captured in a way that would generate additional property taxes. But boy, I haven't really given any thought to that. Ray, I don't know if you have.
Yeah, I was going to say something along the same lines. If you're talking about property tax, there's some kind of assessed value of the system that the tax is usually based on. And so a lot of it might depend on, if you're replacing a very large, expensive power plant with a relatively inexpensive storage system, then no, the tax base would be significantly less. But yeah, no, I haven't thought of that scenario very much either.
Yeah, I guess the only thing is if it's at the end of its useful economic life, then it goes from, a much higher property tax impact to a much lower one, but at least it's not eliminated altogether in terms of the value of the plant. But yeah, we haven't given that too much thought, I don't think.
Excellent. Well, thank you for your response and speaking to that to the level that you can. Any other questions at this time? And again, feel free to unmute yourself and ask if you feel comfortable.
I will add something to the tax question. So property tax is just one way to basically tax the system. New Mexico is considering, looking at incentivizing larger deployments of clean energy, but then also looking at other mechanisms to try and replace lost revenue from natural gas and oil taxes. So states are starting to think about, how to maybe replace revenue from one source with another source. So property tax might not be the only mechanism to, gain some benefit for the state or locality.
Excellent.
Kevin, this is Howard. I have a question.
Yes, go ahead, Howard.
It's for both of you guys, Ray and Patrick. It seems to me that the new transmission required to accommodate all of the energy storage that we need is the big wild card in all of our calculations about the future, and that it's really very poorly quantified. Now, is that right? Do you think that that's true? Is that something that requires lots more study, or is it just not that big a deal?
Ray, do you want to take the first shot?
Sure.
I know you're a transmission expert, so. Yeah,
I'll take a stab at it. So I mean, one way to look at it is, we have to build a transmission, and we build the transmission first. That's step one, and then step two is figure everything else out. I'm not a big fan of that approach. I really think, as I mentioned in my presentations, there are trade-offs between the amount of storage, the amount of curtailment, and the amount of transmission. And so you really need to kind of take a systems perspective and come up with like an overall lowest cost solution. So I guess that's how I prefer to look at it.
Yeah, and I'll just add to that, transmission value is something that we're studying for large-scale pump storage hydro. So for a large-scale pump storage hydro system, when we talk about LMPs or those nodal energy prices, those actually break down into various elements. So there's an energy component, there's a congestion component, right? And there's losses. California, there's emissions that you build into that value. So it's an interesting question because we're modeling it in various capacity expansion models and production cost models, and what we show is that we can actually reduce the congestion components because you're alleviating congestion in all these connecting nodes, which allows more energy to flow from more generators at a lower price to where it needs to go. But effectively, if you're then bidding into energy markets, you're sort of undermining the profit potential because you're actually reducing regional energy prices, which from an energy storage operator's perspective is actually bad, right? So it's an interesting question and challenge, I think, because there are transmission, congestion relief, and deferral benefits that may not be monetizable that actually reduce the profit potential for a pump storage hydro system trying to engage in energy or ancillary service exchanges in the market.
Excellent. Well, thank you, Patrick and Ray, for your responses there to Howard's question. Looking at the time, I'd say we have time for one more question before wrapping up. I want to thank those of you that have been able to stay and participate in the Q&A discussion a little late after was scheduled today. So is there any other questions for Patrick or Ray? All right, well, with that, then I just want to say thank you to all our speakers today, and thank you to Dr. Zhuk and the U.S. Department of Energy's Energy Storage Program as part of the Office of Electricity and Energy Storage. I want to encourage all of you to please register for our next webinar coming up July 22nd at 10 a.m. to 12 p.m. and that will cover energy storage applications and case studies. And again, thanks to everyone and have a great day.